Okay, so honestly, that stuff, since I think you've seen it before, I'm gonna just let you practice it. We'll come back to it on Tuesday. Um, so let me just open it up, see what kind of homework questions you guys have, because there's, I guess, 9, 5, and 10, 1, if you have questions.
Could we go over number 17 on 9.5? It's finding the area.
Right. Okay. So start with the basic one here. Right. So it's probably not a bad idea to draw it. So I know that it's one of these. It's a circle. Which I probably could go, oh, it's a circle. So let's see, the area is pi times the radius squared. The radius is halfway, so that's pi times 2. So the answer should be 4 pi if I work it out. But that's not really going to be super helpful for the other problems. So you can practice that. So the formula for area is the integral of from the lower bound to the upper bound of 1/2 times the function squared. Now, in order to figure out what the bounds are, I need to look at angles until the entire curve is traced out. So I know that if I plug in, we can just maybe come over here real quick and just do a couple points. When theta, 4 sine theta. When theta is 0, I plug it into here, and I will get 0. So I do start, there's when theta, I start at the origin. When theta is, say, pi over 4, just for kicks, substitute that in. Sine is square root 2 over 2. So I'll have 4 square root 2 over 2. So that's 2 square root 2. So I go 45 degrees. I'm going to get him down. And I go 2 square root 2 units out. So I'd be right there. At pi over 2, well, that's the easy one. Sine is 1, so that's 4. So I'm at the top at 90 degrees. If I go 3 pi over 4, then it turns out I will also be at 2 square root 2, and that sort of makes sense. I'm over here, 3 pi over 4. But here's the catch, is when I do pi, I'm right back to the origin because the sine of pi is 0. So the answer, even though it looks like it wraps all the way around for 360 degrees, the bounds are not 0 and 2 pi, they're 0 and pi. If I did all the way up to 2 pi, I'd actually be wrapped around and then I'd wrap back around again. So you really do need to trace this out and watch where the angles go slowly, and boom, when they close the region off, you're done. So I don't know if that, sometimes that's part of the problem, is you like double the answer in the end. But at least that's a setup. So that's a key. That's like on a test that'd be like 7 out of 10 at least, if not more, depending on the question. The rest is more Calc 2-ish stuff. It's important, but sort of making sure you can understand all of the pieces, not just plug in this, but the bounds are tricky. So let's see, if I was to square this out, I would get sine squared. I'd also get 16, so I'd have to square the 4, but it's multiplied by 1/2. So that's 8, which I could either put inside or I could put outside. Yeah, I'm not sure where I need it, so usually I pull constants outside. And then 0 to pi. So, what do you do with that? Well, I don't know. You can look in the back, and in the table there is possibly a formula for sine squared and an integral. There is. So if you want to just use the table, this would be 8 times 1/2 theta minus 1/4 of the sine of 2 theta. And again, this does come out from a basic identity that that sine squared is equal to 1 minus cosine 2 theta over 2. So it's a double angle formula, or yeah, double angle formula identity in order to get this. So you just substitute that in and integrate. And we plug in 0 and pi. So when I plug in all of these pieces, plug in pi, I'll get 1/2 pi. And I plug in pi into sine, I get 0. So that's the first part. And then plug in lower bound. I get 0 minus 0. So basically everything is 0 except for the first term. So that's 8 times 1/2, which is 4. And that there's your answer, which is what you would have expected just using basic area formula for circle.
So for this one, sir, and similar ones on the test, would you need us to solve out using the integral how to do this? Or could we just make the assumption that, you know, the radius is 2 squared and
It'll depend. I think for these, I wouldn't just say, hey, find the area because it's this, because it doesn't really practice this. So if it was a circle, I might say, well, work it out anyway just to show that you understand it. Because I could have given you, I could have just changed this to 1 plus 4 sine, and then the whole thing gets much, much harder. In fact, I think there's at least a couple like that. But at least, yeah, in your head, you're like, oh, I know the answer. So when I work this out, I get the right answer, which everyone loves, right? You work it out and you get like 9 pi, and you're like, come on, it's not cool. Or I do it again and then I get 20 pi, and I'm like, I'm going to do the next problem.
Will we be allowed to use the table on the test?
It's in the book.
Okay.
Yeah. So everything at the end, it's got all the trig identities and integrals, derivatives. And then, you'll even have all those, yeah. So I'll just say, yeah, you'll have all the formulas.
Okay. Thank you.
Mm-hmm.
Sir, can you go over problem 9 for 9.5?
Okay.
what bothers me about that problem is like the numbers you get aren't really like nice numbers. You're like, am I doing something wrong the whole time?
It's possible. Okay, so something about theta equals 3. We want to find the slope, and then of course tangent and normal lines. So we go back and we're like, let's see, the slope has this formula where, I never remember it myself. I always sort of rederive it in my head. It's got sines and cosines in it and derivatives, and yeah, so probably should just remember that myself. Here's sine and cosine, and here's cosine and sine, and this will be a plus and this will be a minus. And then we got to fill in the parts where this is the derivative in each place and this is the function in each place. So I get sine of 4 theta there, sine of 4 theta there. And then I take the derivative of this. This will be 4 cosine 4 theta, and this will be 4 cosine 4 theta, like that. Now, at the same time, we come over here and say, we know that x is equal to r cosine theta, so that will be sine 4 theta times, oh, that's nice, times the cosine theta, and then y is r sine theta. So if I stick the r in there, I get sine 4 theta sine theta. So yeah, it really is just plug pi over 3 everywhere. And that'll give me x, it'll give me y, it'll give me the slope, and then I can just plug that into my slope formula. So let's see. Maybe I'll start with x. So x will be the sine of 4 pi over 3 times the cosine of pi over 3. I'm just taking this formula here and plugging in pi over 3. And 4 pi over 3 is in the bottom quadrant. I think that's negative square root 3 over 2. Cosine is a half. I think you should get negative square root 3 over 4 for x. And for y, I think I can just stick it in here. Sine of 4 pi over 3, I already got that one. That's minus square root 3 over 2. The sine of pi over 3 is positive square root 3 over 2. So I should get minus 3/4. Again, pop in if I'm making an error somewhere. Yeah, so pi over 3 is 60 degrees. That's when cosine is the smaller one. Okay, now the fun part here. Slope. Got 4. The cosine of 4 pi over 3 is negative a half. Wrapped around to the third quadrant. Sine of pi over 3 is square root 3 over 2. That's that one. Sine of 4 pi over 3, I got that in here, so that's negative square root 3 over 2. Cosine is half. And I think I got all the parts to put down here. So this is 4 minus a half, 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 minus negative square root 3 over 2, square root 3 over 2. Whee, that looks like fun. So simplifying down. No, I don't know. I mean, in my head, I don't like all these halves in here, so I could multiply the top and the bottom by 4 and just cancel every denominator out. But that might be confusing to do. So we'll just do it here. So this is negative square root 3, and then the top will be 4 and the bottom is 4. This one is minus square root 3 over 4. This one looks like it's minus 1. And this one is 3 over 4 with the 2 negatives, so plus 3 over 4. So here's the sneaky trick. Let's just call that M. And then tangent line will be y minus a negative 3/4 equals m times x minus a minus 3 over 4. And then the normal, to get the normal line, I just replace that with negative 1 over there. So trying to chase all this stuff out and cancel the 4s out and get a nice common denominator and stuff. You could do it. I guess you could. Why don't I just do that? That isn't too complicated. How does this simplify down here? So if I multiply, I'm just going to go ahead and do this. Multiply the top and the bottom by 4. Then I'll get negative 4 square root 3s. I'll get another square root 3. And the bottom will be negative 4 plus 3. So yeah, this isn't too bad. The top is negative 5 square root 3s. And the bottom is negative 1. So negative, negative, I'll just get 5 square root 3. So that wasn't too bad. I just put in 5 square root 3. That's in the slope. If I didn't make any errors. So yeah, if it looks a little funky, yep, it does. Don't round all this stuff out. Yeah, I mean, trying to get like, that's approximately equal to 8.7. I don't, that doesn't help me. This sort of does. Anyway.
Sir, could you run through number 10 on 10.1?
Yeah. Ah, okay. All right. X squared plus y squared plus z squared plus 4x minus 2y minus 4z plus 4 equals 0. Okay, so the standard form, which I think we could probably put here, standard form, is x minus, I'm just going to put this, the x coordinate of the center plus y minus the y coordinate of the center plus z minus z times z squared, z minus the center squared equals r squared. So it looks a lot like the circle, except now it has this extra z part on it. So x minus h, y minus k. I could do z minus l, but then I realized I don't really like that. It looks like a 1. So we'll just call the center x1, y1, z1. So I need to convert it into that form. So like we did for the circle, if I have an x squared and an x, then in order to get this down into a square form, I'm going to have to do, in this case, 3 complete squares. 3 times. So let's put the x's together. I got x squared and 4x. Leave a little bit of space. We've got y in 2 places, y squared and minus 2y. And then we've got z in 2 places, and z squared minus 4z. I didn't leave myself quite enough room, but that's all right. So what happens when I want to try to complete the square on each one of those? So I take half and I square it in each case. So I take half of 4 is 2, I square that, so I'm going to have to add 4 to this side, so I'm going to have to add 4 to the right side. The second one, I take half of the negative 2 and square it, I'm going to have to add 1, so on this side I'm going to add 1. And then the same thing here, I'm going to add 4, and be careful, it's minus 2, but it gets squared, and I'm going to have to add 4. And now don't forget this one here. That 4 right there, if I brought it over to the other side, it actually would be subtracted. So the 4 with the minus came from the original formula. The other 3 came from 3 complete the squares. So if I do actually complete the squares, this will be x plus 2 squared here. The second one is y minus 1 squared. The third one is z minus 2 squared. And on the other side, I've got 4 plus 1 plus 4, but minus 4. So if I do that right, that should be 5. And now we're in the nice form that it is a sphere. The center is at negative 2, because remember they have a built-in negative. So if I have plus 2, this is minus a minus 2, and then 1 and 2. And the radius is square root 5, because this is r squared on the right side. That makes sense? Cool. All right, what else?
Sir, I had another question on the last homework about 24. Is it saying to isolate that middle region between the
Yeah.
two enclosed areas?
Yes.
Is that I mean, I understand how to get the area, but then when it said to isolate the middle region, that was really throwing me for a loop.
Yeah. No pun intended there. Yeah. This is honestly one of the trickier ones. You really have to know exactly when you put the stuff into the area formula, what are you getting? So if I drew the picture, this is this thing called a limison. It's got an inner loop on it. And if I draw this on the theta axis again, it kind of looks like it's going to be a circle, but then it goes past, and then it loops around like that. So it kind of looks like it's going to spiral in. But then because it's symmetric, it spirals back out. I think I'm going to frame that one. That one looks pretty good. So what you really want to do is figure out the stuff that's outside of this. Don't include this little loopy part in here. You want stuff that's on the outside. So just like that. Now, in order to do this, I need to know what the bounds are. Like, where am I on the graph at different angles? So if I made my chart again, let's see. If theta is 0, yes, I'm here. The problem is if I drew a straight line from there, I would fill in both the inner loop and this outer loop here together. So if I went theta equals 0, I would get everything from 0 out to the outer one, includes the middle piece here. At pi over 4, let me just make a small chart over here. So at 0, I'm at 3. At pi over 4, plug in pi over 4, I get square root 2 over 2, and the 2's cancel, so I'll get 1 plus square root 2. So that's about here. So if I did the area, here's the catch. If I did the area from 0 to pi over 4, I would get this entire sector out to this curve. So it would fill everything in, including the part of this. And that's definitely not what I want. I want to somehow deal with the fact that I'm counting this part as well. Just 3 more points, and then I think we can work from here. If I did pi over 2, so if I went straight up, then I plug in pi over 2. Cosine is 0, so that part drops out, and I just get 1. So that at least makes sense. And then when do I hit here? Like, when do I wrap around and get to the origin? Because I think that's going to be a point of interest. And so I need this whole thing to be 0. I need the radius to not go out at all. So in order to get the radius to be 0, this part has to be -1, which means the cosine has to be -1/2, which means I'm at 2 pi over 3. 120 degrees. Now I'm in the second quadrant. Cosine is -1/2. When I plug it in, that'll make this -1, and it cancels everything out. So that's when theta is 2 pi over 3. So if I did this integral from 0 to 2 pi over 3 of the usual thing, 1/2 or 1 plus 2 cosine theta squared, what I really would be getting is I would be getting all of that, the entire top half, including the inner part of that loop, which is clearly, that's too big. I don't want to include the stuff on the inside. So the only way to really deal with that is then subtract off the part that I don't want. I mean, technically, this is like, if I doubled this, I'd get the entire interior. So I could double it and get the entire interior, but then I want to take away the stuff that's in here. So I need to figure out what angles correspond to this inner loop in here. And so it's probably, if I continue to follow around to get to this point right here, that's when the radius is 1. Well, it could be either 1 or it could be -1. And in fact, if I continue around from this, all these cosines are going to be negative. So I can see that when I hit pi, again, this is the tricky part about polar. I go 180 degrees, I'm facing to the left. But when I plug in pi here, what happens? This will be -1. Multiply by 2, that's -2. I add 1, that's -1, which means I take a step back. So I rotate around 180 degrees, I'm facing to the left, and instead of taking a step forward, I take a step back and I'm here. So if I did the integral from 2 pi over 3 to pi of the same thing, 1/2, 1 plus 2 plus n theta d theta, what I would be getting is that little part right there of the 1. So I'd be getting the lower half because I'm wrapping around 2 pi over 3, then I start going below and I get to here. So I'd be getting this little piece right here. So I don't know if it's clear that all I need to do is if I took twice the first one, I'd get the entire shape with this filled in. If I did twice this one, I would get the entire inner loop filled in. And so all I need to do is then subtract those two. And that would be not the area that I want. It can be the outer part. So this is, you know, the hard part on these look like, wait, is the hard part the integral or is the hard part finding the bounds? And often they're split. Like, you know, finding the bounds, you really have to trace this stuff out. Filling in, filling in, filling in, filling in. With 2/3, I get the entire thing. Filling in, filling in, filling in. I only get the lower little piece here. And based on symmetry, those are the same. These are the same. So I got to figure out those two integrals and then subtract. So at least that's the setup.
Thank you, sir.
You want to go through the actual calculation, or
I don't need to. I can do the math. I was just struggling to isolate those two.
right? Yeah. It really does come down to drawing the pictures, figuring out which part of the curve, or if you have two curves, which curve corresponds to which one, and really know that it's filling in every single time as you go in with these rays, including the part maybe sometimes you don't want. But, so now. Ah, totally disable my pen every single time, and for some reason the buttons come back on. So I do some math somehow, and then I get whatever it is. I suppose you can estimate it by doing circles. It's an area that's a radius 3, or radius 3/2. So square that, I get 9/4 times pi. Maybe it's around that. 9-ish. No, I don't know. Somewhere in there. I wouldn't be surprised if it was 12, but I'd be surprised if it was 40. You'd probably get an answer that did something wrong. All right. Anything else? What do you got? Maybe you're leaving the homework for today. But again, it's due at 1, and there are 2 sections, so make sure you get that stuff done. I have graded the homework basically on, you know, if you turned it in and you did all the problems, it'd be 10 out of 10. That definitely does not mean you got them all right. So I've made comments in the comments section on the side. Definitely go back and read those. Don't just look at the grade and go, oh, I got 10 out of 10. Everything's great. Because there are sometimes lots of comments. I do appreciate all the effort. I think it is super important to work this out on your own. Find snags, come back, ask in class. That's sort of a non-punitive way to get feedback. Anyway, yeah, so anyone else holding out here? Scared to pop up?
Sir, can you real quickly go over problem 28 for the same unit?
28?
Yes.
Yeah. Okay, right, okay. So same idea here. So the picture's already been drawn, but as usual, it's a good idea to do it. I've already messed it up. Oops. No, I think I can just do this. Right. I need to move the axis over there a little bit. So this is a cardioid. In this case, it starts at 0. And I'm going to emphasize it a little bit just because the picture is kind of small. And then this is a circle. Comes out here to 1. And still make it a little bit bigger. And the part that I want is that area right there. So you can see that if I start drawing radial lines out, for a while, I'm only hitting the heart shape. I'm only hitting the cardioid. Until I hit this point right here, which I think is going to be of interest. Then when I keep drawing the rays, I'm going to only be doing the circle. So I think it's probably wise to do this, where I just take this, and I'm only curious about that part right there. So that's like divided in half. That's the lower half, which only deals with this curve. Plus, I do the circle, the upper half. And I put those, that's the upper half of this picture, and that's only on the circle. So really, I just needed to figure out what this angle is here, and then I can do one area for the circle and one area for the cardioid and just put them together. So I do need to know where they hit at that value right there. And so in this case, I hope I can just set them equal to each other. Again, in the intersection problem, you have to draw the picture, and you have the picture, so you could eyeball it, I suppose, but let's see if we can just set them equal to each other to figure out where they hit. And in this case, it's not too bad. I could add cosine to the other side. I got 2 of them. So that means cosine has to be half, which means that the angle is 60 degrees or pi over 3. So that makes sense in my picture. It does. It is pi over 3 where they hit. I think the starting point for one will definitely be 0. Now I got to figure out when does the circle get back around. So let's see. I'm pretty sure that this one here is going to be going from angle 0 to angle pi over 3, and that'll trace that out. Here, the angle is going to go from pi over 3, and then when does it come back and get down to the origin? Well, I think when this will be a 0 radius when the angle is 90 or pi over 2. So that would be maybe kind of what you expected anyways. This thing kind of wraps 0 to pi over 3 and then pi over 3 down to 90 or pi over 2. So now we just got to set up those 2 areas here. This one will be integral 0 to pi over 3 of 1/2 1 minus cosine theta squared. That's like the lower half of whatever this kind of football-y shape looks like. Plus, and then I do it for the circle, 0 to, oh, ruin it right there, pi over 3 to pi over 2 of 1/2 the curve, which is cosine. So again, setup is difficult, figuring out which curves, which angles. In order to work this out, we're going to have to multiply some stuff out, using either trig identities or some tables. But the rest is sort of the integration steps, making sure don't forget the half, plugging in the values correctly, squaring the minuses out correctly, things like that. And even though this has a cosine squared and this has a cosine squared, you can't combine them because the bounds are different. So you're going to have to work this one all the way out. You're going to have to work this one all the way out. And I don't think I know it, you know, if there's like, is there a shortcut formula for that, for a circle? Yeah, I guess probably, because the entire top is a half circle, so I can figure that out. And then this side over here is a sector, and I know the answer for a sector, and then I can subtract the two. If you wanted to use some basic geometry, you could probably figure out what this piece is cut with this chord here. You don't have to, because you can just do the integral and work that out, but intuition-wise, you can take the entire thing as a half circle with that, and then you can figure out this sector, which I gave you that sector equation last time, and work it out. You should get the same answer.
How did you know that the top part was pi over 2?
This one here. Right. So we know things are going to start at 0 because both of the curves start at 0. So if we went 1 degree, 2 degree, 3 degree, 4 degree, and we're filling this out, once we hit 60 degrees, we've hit the intersection point. Now, if we just follow the circle and we go 61 degrees, 62, 63, and we just keep going and plugging in more and more and more values, it's going to come down here. And when we plug in 90, we hit the origin. Yeah. It'd be nice
that
to.
makes sense.
Yeah. Okay. Cool. So yeah, I mean, you could, you know, on your calculator, if you want, you can do a table function which goes like 1 degree at a time, and you can really watch it go super slow around, and sometimes that's instructive. Because what do? We plotted like 3 points, and we're like, well, obviously it's this. But if you want to plot, you know, 20 different points, you'd be like, okay, I see it. It goes chuk, 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 here, and then it goes chuk, 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 down to there. There you go. Now, the other thing I'm wondering is do you think that like these two answers are the same? Like on one side, it really is symmetric on one side, and then the other? I'd be careful on that one because the circle, like the curve of the circle versus the curve of the cardioid are slightly different. And the way I've drawn it looks symmetric, but I don't think so.
Yeah, I don't think it can be symmetric because 0 to pi over 3 is 60 degrees, right?
Yeah.
And then from pi over 2 to 60 degrees is 30. But you have the same, like the same 1/2 actually.
I hear what you're saying, yeah. Although you don't, maybe the fact that the circle is curved differently, that, you know, you change the angle, but you're also changing the shape. So maybe somehow they balance each other out. I would guess they're fairly close, but I would be really surprised if they were the same answer. Yeah, for both of those reasons. So yeah, I mean, I know these problems can be difficult because you still get around to the sake of like, how do I even plot that again? If you can't get that quite right, like, you know, you forgot to put your calculator in radian mode. It's gonna look bizarre. So make sure it's in radian mode. Make sure you plot enough points. Make sure, because if you don't plot enough points, you can get something jagged, disconnected. And so it takes a while to get even the curves. Now I got to figure out like in the intricacies of the area. Yeah, I know. It takes a lot of practice. So I would recommend doing a bunch of these. All right, what else? Going once. Well, how about this? Why don't you go practice this stuff, and you know, in between now and 1 o'clock, if you have questions, just ping me. Either, you know, email, text, or yeah, one of those two, and I can hop on. We can chat. Otherwise, I'll let you guys have time to go work on this stuff, and we'll. You know, if I don't see you today, I'll see you Monday morning. So have a great weekend. Rest up and study up. So we'll probably stop there.
Have a good day, sir.
Yeah.
Have a good day, sir.
Thank you, sir.